All right, so we are talking about paths. Your confidence for this particular chapter begins with paths. How are you feeling about paths? And we talked about length, the length of a path, and then we talked about a specialized type of path called a cycle that begins and ends in the same node, and cycles also have length. So that is our confidence so far for this time being. So what we want to do is we want to see if we can use paths to define new relations. Can I, starting from a path, define new relations? We're going to see that we actually can. So if I have some relation R, I can actually define a new relation with the path. Let's say, for instance, the relation R squared. And I would say that R squared is defined as the values, the ordered pair A and B is in R squared if and only if there is a path of length 2 from node A to node B. So paths of length 1 are automatically implied by the original relation, because a path of length 1 is a path from A to B that defines the ordered pair, the relation between A and B. But R squared, the relation squared, is defined as a path of length 2 from A to B. I can find a new one. So let's say, for instance, that I have some relation R.
Is it path of what? Oh, length equals 2.
Of length equals 2. That's my shortcut for saying length equals 2.
Yeah.
So let's say, for instance, that I have some relation R that is, I'm pretty sure we might have already talked about this one. I'm going to have 1, 2, 2, 2, 2, 3, and 3, 1. These are already paths of length 1. Length 1 from 1 to 2, from 2 to 2, from 2 to 3. These are already paths of length 1 if I were to map them out on a digraph, correct? The new relation R squared would say that there is a path of length 2. So I could say R squared is paths of length 2. If I were to draw 1, 2, and 3, I can see that there is a 1, a 2, and a 3. If I'm going from 1 to 2, and from 2 to 2, from 2 to 3, and from 3 back to 1, paths of length 1. Excuse me, paths of length 2. This already implies paths of length 1. So let's see if we can find paths of length 2 from node 1. From node 1, can somebody tell me paths of length 2 from 1? From node 1. It would have to start at 1. And the only place that 1 goes is, see, I like those arrows. That I don't know if I can draw that classy of an arrow. No, not going to be able to do it. So 1 only goes to 2, which means that any paths of length 2 are going to have to go from 1 to 2. And where does 2 go? It looks like 2 goes to 2, and it looks like 2 goes to 3. Excellent. So it would seem that in this digraph, or in this relation that is squared, that I am going to have 1 to 2, because there is a path of length 2 going from 1 to 2. And I'm also going to have 1 to 3, because there is a path of length 2 from 1 to 3. Let's see if we can go to node 2. Paths of length 2 starting at 2. It would have to start at 2. 2 goes to 2 separate places. So I see 2 to 2 to 2. And where else does 2 go? So 2 also goes, or we can say 2 to 2 to 3. Where else does 2 go? 2 to 3 to 1. Does it go anywhere else? All right, which means that if I'm looking for paths of length 2, that we should also have 2 to 2 on here. It looks like I should also have 2, 3 on here, and I should also have 2, 1. Because it says that in order for this to be an element in R squared, there must be a path of, it says, AB is an element in R squared infinitely if there's a path of length 2 from A to B. So when I put R squared, my first ordered pair in R squared is 1, 2. That means there must be a path of length 2 from 1 to 2. And that's what we defined up there, right? When I was mapping out paths of length 2 for node 1, that's the very first one. I pick up the first node and the last node in the path of length 2, and that becomes my new ordered pair. So I guess if we're going to be complete, let's do the last node 3. I'll put him over here. Paths of length 2 from 3. Are there any paths of loop 2 from node 3? Node 3 only goes to one place. Does that word go anywhere? Yeah. So it looks like there is only one path of length 2 coming out of node 3. So I'll add that. The first and the last pair, 3, 1. Oh, thank you very much. That's 3, 2. 3 to 1 to 2. 3 to 1, 2. So I have defined a new relation called R squared. The new relation does not have the same elements as the old relation, right? I'm going to look at the old relations, 1, 2, 2, 2, 2, 3, and 3, 1. I see some of those in here. But I don't see 3, 1. So we got rid of 3, 1, but we did add 3, 2, and it looks like we added a couple more because there are additional elements in there. So I have a brand new relation called R squared. And R squared is defined as the element AB where there is a path of length 2 from A to B.
So would R cubed be the same thing, just path of length 3?
Say it again?
Would like R cubed?
Yeah, that's an excellent question. You're asking the question, what about R cubed? R cubed is going to contain this, the element AB will be an element in R cubed if and only if there is a path of length equals 3 from A to B. I could continue this conversation that AB would be an element in R to the 4th if and only if there is a path of length equals 4 from A to B. And so on and so forth. I'm actually going to take this one final step down because as you just may imagine, I could have R to the 5th, R to the 6th. I'm going to take this R infinity. And I'm going to say that AB is an element in R infinity, but this time I'm going to change the rules. This time, instead of saying if and only if there is a path of length infinity from A to B, what is the problem with that statement if I were to write it down? R infinity is the relation that contains the the ordered pair AB.
It must be a finite path.
Because paths are defined as finite. There cannot be a path of infinite length. That violates the definition of the word path. Paths are, by their very definition, finite. So the rules are going to change here. I'm going to say that AB is an element in R infinity if and only if there is a path of any length from A to B. So R infinity is actually what is called the connectivity relation. It has a special name. It's called the connectivity relation. And it begs the question, does a path exist? Can I get from here to here on a path of any length at all? Is this node connected to this node at all through a path of any length at all? And the connectivity relation becomes critically important in, I don't know, let's say, for instance, computer networking. If I have 15 nodes on a network, and the question is, can I get from here to there through a path of any length? Especially if one of the nodes happens to be like the printer. Can I get to the printer from that machine over there? Well, no, you cannot. That could cause a problem, right? Can these two nodes communicate through a path of any length at all? Are they connected through a path of length 1 or length 5 or length 875 through a path of any length at all?
Wi-Fi could be linked to 1 if you want to.
Say it again?
But Wi-Fi can be linked to 1 if you want.
Wi-Fi. All right, so let's just give this a try. I'm going to expand on this example just a little bit. So we kind of drew it out for ourselves right here. As a matter of fact, there is this idea, this principle, the fact that I can use a relation R to define new relations, relations squared, relations cubed. This is a part of that PowerPoint presentation, which says that R squared defines a relation where A and B have a path of length 2. So when I look at the relation, the digraph, the matrix, and I see a set of ordered pairs for R squared, it is a path of length 2. I didn't put length R cubed, R4, but then R of k would say that, the generic, that AB is an element in R of k if there's a path of length k. So that would be squared or cubed or to the 5th, to the 19th. Finally, it brings us to this thing called the connectivity node, or the connectivity relation. This says there's a path of any length from A to B. Because we cannot have a path of length infinity, it must have a finite length. This is going to tell us whether or not there's a path of any length. All right, so let's come down here and look at this a little bit more. We'll explore this one a little bit more. I see that we came up here and we had this relation 1, 2, and 3. And from there, or I drew the digraph. There was my relation right here. And from there, we drew the digraph, right? I can see the beautiful digraph of it right here. What I'd like to do is I would then like to expand that because a relation has a digraph and it has a matrix. Which means that I should be able to map a digraph for R squared. So I'm going to come down here and I'm going to draw a digraph for R squared. So we have 1, we have 2, and we have 3. 1, 2, and 3, the same values as my R. I'm going to look at the individual ordered pairs, and I see that we can go from 1 to 2, and I see that I can go from 1 to 3. I see I can go from 2 to 2. There is a path of length 2 from 2 to 3. There is a path of length 2 from 2 to 1, and a path of length 2 from 3 to 2. So relations have digraphs, relations have ordered pairs, and relations have matrices. So I could draw the matrix of this as well. So one of the ways that I can find paths of length 2, it would seem one of the ways is I could draw up the digraph and I could just start listing out all paths of length 2. That's exactly what we did, right? Seems like that's one of the ways that I could go about finding all paths of length 2. I'm going to add one additional step to this. One additional step to this is that not only do relations have ordered pairs and relations have digraphs, but relations also have matrices. So I'm pretty sure this is 1, 2, 3, this is 1, 2, and 3. And what I'm going to do is I'm going to map the matrix of the original relation. I'm going to have to look over here, 1, 1, 1, 2, and 2, 3. 1, 1, 1, 2, and 2, 3. Did I get those right? 1, 1, 1, 2, 2, 3. Let me check it again. 1, 1, 2, 2. Nope. 1, 1, 2, 2. And there's 2, 3. I can see it right there on the edge of my page. 2, 3. And then the final one is 3, 1. There we go. So I have the ordered pairs, I have the digraph, and I have the matrix. I will fill this in. That is the matrix of the relation. I'm also going to generate a matrix of this relation as well right here. The matrix of this relation is still 1, 2, 3, 1, 2, and 3. So this one, it looks like it has 6. Did we have 6? 1, 2, and 1, 3. All right, we'll put 1, 2, and 1, 3. You guys you're checking on me, right? Making sure I'm getting them in the right place. 1, 2, 1, 3, 2, 2, and 2, 3. So I'll put 2, 2, and 2, 3. And then 2, 1, 3, 2, 3, 2 should go right there. Did I get them all in the right place? So there should be 6 of them in total. I'll put the zeros. So the way that I went from r to r squared was I drew a digraph, and from that digraph I mapped out all sets of ordered pairs. There they are. I can see them. I can see all 6 of them. Is there a different way for me to go from r to r squared?
No, just do the matrix product.
There you go, the matrix itself. So what I want to do is I want to take this matrix and I'm going to drag the matrix down. So if you don't mind, I'm going to steal this matrix right here. And I'm going to copy it. I'm going to drag it down here so I have a little bit more room somewhere over here. So if this is the matrix of the relation, it would seem like if I multiplied the matrix of the relation by itself, that m of r multiplied by m of r would give me m of r squared. So this is 1, 0, 0, 0, 1, 1, 1, 0, 0. If I'm going to apply my comparable matrix multiplication, these are Boolean matrices, so I'm going to do the Boolean product on them. We're going to have to find all of these 9 individual values. It looks like it is going to be, since this is a 3 by 3 and this is also a 3 by 3, can I multiply them together? Yeah, because I see that the inside is the same. If the inside is the same, that means the outside is the size of the answer matrix, which is a 3 by 3. So I'm going to have to find each one of the individual values. So one of the ways that I can do it, I said that there was a shortcut. So if I'm trying to find this one, I am looking for row 1 and column 1. Is that row 1 and column 1? Did I get them right? And I'm just looking for pairs. Remember I said the shortcut is if when I lay them side by side there are pairs of 1, automatically I know the answer is what? 1. If there are no pairs, the answer is 0. So all I have to do is lay them out side by side. So I'm going to do the same row, 1, 0, 0. This time I'm going to try to find the second column, 0, 1, 0. What can you tell me about the answer?
0.
It is 0. Very good. So we'll do it one more time. 1, 0, 0. I'm going to lay out the last and final column, 0, 1, 0. What is the answer? 0. Excellent. So it is a shortcut. Seems to be a little bit different way that I can do it. So that was row 1. Let's try row 2. Row 2 is going to be right here, 0, 1, 1. So I'm going to start with 0, 1, 1, and I'm going to begin with column 1. If you don't mind, I'm going to put column 1, 1, 0, 1. What is the answer? I'm going to put column 2. Just to make my life faster, I'm just going to drop column 2 beside it. 0, 1, 0. Are there pairs of 1s? Yeah, there's a pair of 1 right here. Yeah, so what is the answer? 1. So then I'm going to drop the third column beside it. 0, 1, 0. Are there pairs of 1s? Yes, there's pairs of 1s right here. So we'll do it for the last and final row. The last and final row is 1, 0, 0. So this is going to be everything that I multiply. The first column, 1, 0, 1. Are there pairs of 1s? Yes. And then we're going to have 0, 1, 0. Are there pairs of 1s? No. And then the last column was 0, 1, 0. Are there pairs of 1s? No. So this is, does everybody agree with me, although I did it fast and I used the shortcut, because the whole doings of the meets and all of the ands and the ors freaking me out. So I'm just going to lay the column and the row side by side, the row and the column side by side, and I'm looking for pairs of 1s. Because my anding and my oring skill would tell me that there has to be a pair of 1 in order for the answer to ever be 1. And it doesn't matter how many pairs of 1s there are. If I had laid out 1s, 1s, and 1s, what is the answer? If I had 3 pairs of 1s, what is the answer?
1.
If I had 18 pairs of 1s, what is the answer? So I don't care how many pairs, I just need a single pair, at least one single pair of 1s when I lay the row beside the column, and it tells me what the answer is. So that begs the question, did we just multiply the matrix of the relation by itself? Did I just calculate the matrix of the relation squared by multiplying it by itself? So I want to look at this. And I want to see, all right, cross your fingers, because this is where the rubber hits the road. If this is truly the matrix of the relation squared, then it should be the matrix of the relation squared as we calculated it the long way. All right, there you go. Let me stop the recording now. Try to figure out what in the heck did I just did wrong. Because they should be, that is how I can calculate the matrix of a relation squared, is I can just take, or excuse me, that's how I can calculate the relation squared, is just do the Boolean product on the relation itself. On the
matrix, you mark 1, 1 instead of 1, 2.
Oh man, all right, thanks, you found my error. Where is my error? 1.
When doing the matrix, you put 1.
Oh. So you're saying that I marked my matrix wrong. All right, this is maybe why I want to do it in the Boolean multiplication of the matrices instead of. All right, so you're saying that I got my very first matrix wrong? Oh, you're right, because that is 1, 2. And that's why I need a classroom of students following me out. If that's 1, 2, but I put it here, I put it in 1, 1 instead of, it should have been here. Is that what you're saying, that I got that one wrong? Are all the rest of them in the right place? I'm going to say a more reliable way to do it is to just take the matrix of the relation, multiply it by itself, and it gives you the matrix of the relation squared.
Now it's a graph.
That begs the question, how do you think that I can calculate, if that is the matrix, if this becomes the relation squared, how can I calculate the relation cubed?
Multiply the relation squared by the relation.
Yeah, I'm going to multiply the matrix of the relation by, so I'm going to multiply the matrix of the relation by itself, and I'm going to get an answer which I am then going to multiply by the matrix of the relation again, and it is going to give me matrix of the relation cubed. I know how to go from a matrix to the set of ordered pairs, right? If I can start with a set of ordered pairs and map it to a relation or a matrix, I should be able to go backwards, right? I should be able to start with a matrix and from that matrix find the ordered pairs, right? All right, so that begs the last and final question. Great. I know how to do, I know how to find the relation squared and cubed and fourth and all the way up to the relation k, because I'm pretty sure that when I was looking at that PowerPoint presentation that we had r to the k power means there is a path of length k, but what about r to the infinity? How in the world am I going to say How do you do that? How would I ever calculate this thing that I'm calling the connectivity relation? Because there is no way that I can raise a matrix to some infinity power. I could even do the relation of paths of 85. Just raise the matrix to the power of 85. Just multiply it by itself 85 times.
Couldn't you technically just go until it doesn't change anymore?
As a matter of fact, we're going to have a long, drawn-out discussion about how to calculate that in this chapter, in chapter 4. We're currently in chapter 4, right? So we're going to come back to that. It's called the Warshall's algorithm, but we will come back to that. Because what we need to do is we need to find out properties of matrices, which is in the next chapter, chapter 4. The next section, 4.4, is all about a variety of different properties that a matrix can exhibit based upon things called paths and cycles. We'll cover that next time in class. A very observant student brought to my attention that the reason why my matrix of the relation squared is not matching, that this is not matching with this, is because the original matrix that we started with and multiplied here was off by 1. That this element 1, 2 I had put here when it should actually go here. So what we're going to do is we are going to multiply with the correct matrice. So this would tell me that the matrix should be a 0, 1, 0, 0, 1, 1, 1, 0, 0. Based upon the 4 elements, we should have a 1, 2, which goes there, a 2, 2, which goes here, a 2, 3, which goes here, and then the 3, 1. So this is actually the matrix of my relation. If I multiply it by itself, using the shortcut that we know, I'm going to put this here. So the shortcut means that I am going to start with the first row, 0, 1, 0, and I'm going to do the shortcut by multiplying it by the first column, 0, 0, 1. There are no pairs, so that element will be 0. If I multiply it by the next column, which is 1, 1, 0, I can see that there are pairs here, so that answer will be 1. Let's multiply it by the last column, which is 0, 1, 0. Once again, I can see that there are pairs of 1s, so that value will be 1. So now let's multiply the second row. Here is the second row, 0, 1, 1. So I'm going to multiply that by each one of the columns, 0, 0, 1. There is a set of 1s. I'm going to multiply it by the next column, 1, 1, 0. There are pairs of 1s. And then I'll multiply it by the last column, 0, 1, 0. There are pairs of 1s here each time. So then let's try the last row. The last row is 1, 0, 0. So I'm going to multiply this value by the first column, 0, 0, 1. There are no pairs of 1s. I'll multiply it by the second column. There are pairs of 1s here. And then I'll multiply it by the third column, 0, 1, 0. And there are no pairs of 1s, so I'll put the 0 there. Now we're going to see if the matrix that we generated when we manually calculated all paths of length 2. And now I can see that those two matrices do indeed match, which is the reason why it's critically important that you show your work when you are doing all of your math problems, because the simplest of mistakes can have a far-reaching impact on your ultimate answer.